In this video, we're going to continue with the Bohr model, and we'll focus on the failures of it and how it was modified to get to the Schrodinger model of the atom, the final model that we're going to focus on in grade 12 chemistry. So in the previous video, we saw the successes of the Bohr model. It was able to explain the hydrogen emission spectrum. It was based on a quantized view of the electron, so quantization of the electron's energy in orbits. It was easy to visualize. Now, the issue, though, is that it couldn't really explain all of the atomic spectra. It could only explain it for hydrogen and simple things with one electron, but that's about it. It could also not explain why it was that energy levels existed here, here, and here, but not somewhere in between as well. Like, well, why did the electron have to be here, here, and here? But why couldn't it be in between or in between over here? So Bohr couldn't really explain that either. Just as a quick recap, though, before we go into solving those problems, let's take a look to see if we understand how Bohr related the shells to energy levels. So once again, closer to the nucleus means you have less energy. Farther away means more energy. That's because you're not as tied down to the nucleus. So let's take a look to see if we understand if energy is being emitted or absorbed in different scenarios. So we'll start off with this one over here. I'll start off with scenario B. The electron is jumping from n is equal to 1 to n is equal to 4. So it's going from a low energy to a higher energy. So that means it must be absorbing. Let's take a look at scenario C. In scenario C, it's going from n is equal to 3 to n is equal to 2. So it's going from a high energy to a lower energy level. So it must be releasing or emitting energy. And then scenario A, the electron transitions from 5 to 3. So it's going from energy level 5 to energy level 3. It's going down energy levels, so it must be releasing more energy. So it's emitted in scenario A. Between scenario A and scenario C, think about which one might release more energy. Hopefully you're thinking probably scenario A, because you're jumping down 2 levels from 5 to 3, whereas here you're jumping down 1 level. So there'd probably be a greater release of energy in scenario A, in other words, a smaller wavelength, because a smaller wavelength has more energy, higher frequency. So again, Bohr's model wasn't perfect. It couldn't explain all the spectra. In some cases, we'd have this line spectrum. When we turn on a magnet, we'd have 3 lines, and we didn't know why that was, so Bohr couldn't explain that either. So there were a variety of things Bohr couldn't quite explain, and Bohr's model was also breaking a few rules in physics that we couldn't break, so we had to fix it. So first, we're going to solve the issue of why is it that electrons can exist, here, here, and here, but not anywhere in between those levels. And the way that was fixed is by this scientist named Louis de Broglie, where Louis de Broglie said that the electron, kind of like light, can be both a particle and a wave. So Louis de Broglie introduced the idea of the electron behaving as a wave. And that helps to fix our problem that Bohr had. And why did it fix that problem? Let's take a look. When an electron forms a wave, it needs to connect both of its ends, and they need to match perfectly. If they don't, that wave just cannot exist. This is a wave that formed here. The electron, its ends met and matched, and so that was allowed. So at levels kind of in between here, you just couldn't form a wave. The ends wouldn't match, and so it would sort of destroy itself. It wouldn't exist. So thinking of electrons like waves, that allows us to solve the first problem, to explain why certain orbits are allowed but not others. So energy level of 3 is allowed, but not 3.3 because it won't match up, and it will just destroy itself, kind of like here. It won't match up there, destroyed. But energy level 3, a wave will form. 5, a wave will form, but not kind of in between those. So only integer wavelengths were said to be allowed. So one interesting thing about waves is that essentially everything has a wave. You have a wave. This car has a wave. A baseball has a wave. An oxygen molecule is a wave. But they're not really significant for big objects like us or like the ball, because the bigger the object is, the smaller the wavelength. You can calculate a wavelength using this formula here. This is wavelength over here. and this is a constant over the mass times the speed. Notice that the bigger the mass, the smaller the wavelength is because the mass is in the denominator. You don't need to know this formula, but it's just some math behind it. So everything has a wavelength, but for us it's insignificant. However, for an electron, which has a very, 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 very small mass, the wavelength is quite large. So for an electron, it's both a particle and a wave essentially at the same time, a wave-particle duality like light. Now, that first problem there is solved. The other problem with Bohr's model is that Bohr was kind of saying he knew exactly where the electrons were. They exist over here at this point in this shell, over here at this point in this shell, over here at this point in this shell. But you can't know the exact location of an electron. It goes against a principle called the Heisenberg's uncertainty principle. And so that basically says it's impossible to simultaneously know the exact position and momentum of a particle, because while you're trying to measure where the particle is, the electron is, let's say with a microscope, you shoot some light at it so you can see it, you're going to change the position and momentum of the electron. Like it's just going to push the electron and you don't know exactly where it was at that point. So you can't, Bohr is lying when he says he knows exactly where the electrons are. Because according to this principle, the very act of measuring something changes its location. So we somehow have to modify our model so that it doesn't break this rule of Heisenberg's uncertainty principle. We can't lie and say we know exactly where it is. So instead of saying we know the exact location, we're going to now talk about probability. So that brings us to our last model here, the quantum mechanical model of the atom. So here's Bohr. Bohr was able to take information from atomic spectra, Planck and Einstein to make the Bohr model with quantized energy levels. But it wasn't perfect, so then we had to incorporate the wave-particle idea of de Broglie, and the uncertainty principle of Heisenberg to come up with a new model by Schrödinger called the quantum mechanics model, which is going to look at electrons as waves and as regions of probability, not certainty, because you don't know exactly where electrons are. So we're going to take a quick look at this as an overview, and then in the next lesson, you'll see more details on the quantum model. So in Schrödinger's quantum model, we no longer say that electrons exist at certain exact points in orbits. Orbits were 2D paths. They're not a thing anymore. In Schrödinger's model, we're looking at regions of probability that look more like this over here. These 3D regions in space where electrons are likely to exist, we say 90% of the time. 90% of the time around the nucleus. So the origin will be the nucleus, and then these little shapes are the areas of space where they're likely to exist. And these are based off fancy equations that Schrödinger used using some numbers that we'll see in more detail later. So we sometimes call the newest model the electron cloud model, which is a cloud of probability around the nucleus. And so these are not all, a whole bunch of electrons here. Rather, these are snapshots of where the electrons could be. And so in the regions that are darker, you have a higher chance of finding the electron compared to the regions that are lighter, farther away from the nucleus. And that makes sense because the nucleus holds the electrons closer to itself. So what do we see in this lesson? Well, in the previous PowerPoint, we saw the early models of the atom, early philosophers, Dalton, then Thomson, then Rutherford. We then saw how we went from Rutherford to Bohr, by making the model follow more modern physics with quantization. And then we saw how Bohr was wrong. So we had to incorporate uncertainty principle and wave behavior of electrons and start to think of these electrons existing in regions of probability instead. So we have orbitals now instead of these orbits, and these regions of probabilities, they're basically determined by fancy formulas that take into consideration the wave-like behavior of electrons. And here we see Schrödinger smiling because he's happy that he's making our lives miserable with these weird-looking shapes. But we'll see that we'll learn to love them in our future lessons and understand where these come from. But the idea in grade 12 is that we're going to focus on Schrödinger's model. Bohr's model is still good. It's simple, easy to visualize. We can use it to draw some bonds and to show simple concepts. We don't always need to draw it this complicated. We only use it, in certain circumstances. If we want more detailed explanations of certain types of bonds and reactions and shapes of molecules. So really, we can keep it simple sometimes, but in grade 12, we need to learn the more complex model that's a bit abstract, but we'll get to it.